too much things that we covered today, just for the first two sessions, two part of the today we talked about lots of, I should say, implications of the polynomials in action when you have the software and the data you just want to plug it. Okay. Now we just want to study some characteristics of the polynomials, which we call that end behavior. Let me go here. Okay, polynomials and behavior. Okay, now we're going to talk about the polynomials and behavior, or what we call that asymptotic behavior. These are essentially the same thing. In order to talk about these ones, let me pick up a right color. Then, give me a second. Give me a second to make sure that I'm okay. I'm the right page. Okay, yeah. Okay, let me go here. Let me show that to you. I'm gonna plot a function. And now I'm gonna go back. Okay. Now, guys, look at this. Before we talk about the end behaviors and asymptotic behaviors, something which we also talked about that last week, but in brief. Now, in order to talk about that, what do we mean by the end behavior? By the end behavior is this, or asymptotic behavior. When we say that, this is the formal definition of the end behavior or asymptotic behavior of the polynomial function, which is essentially is going to be this. We say that we are always interested, because you see, because the functions that we talk about as a polynomial is always represents us like this format. We say that that y represents a variable which is going to be dependent on an independent variable x, but by a function or by a transformation. We say that if we can, in nature or wherever just we happen to be, if we just find a representation like that we have a variable which becomes dependent, for example, on another variable which is going to be dependent, for example, your income, with respect to the number of the hours that you work, or for example, the temperature, with respect, for example, the time of the day, or for example, your grade of the final math course, dependent on, let's say, as a function of the number of the study that you have. If we represent a transformation like that, or a function which becomes the description of the other, for example, variable, for example, y is being described by the x there, we are always interested to see that how the function behaves. I mean, how, for example, your y action behaves. We call that y behavior. When x, let me put that into the words. It's gonna be much better. we said that you're always interested to find how the, I call it y here, which means that the dependent variable, how the y or the function behaves when x gets larger and larger and larger. You see, that's the definition of the asymptotic behavior or endpoint behavior, that you're always interested to see that. For example, what is going to be the value of the y when x becomes larger and larger and larger? That's what we call that asymptotic behavior. For example, you said that what is going to be the grade which I'm going to get for the advanced functions 12 in the final exam if I study more and more and more and more hours. It means that you are coming to see the end behavior, the final outcome, or the end behavior or asymptotic behavior of your dependent, I should say, variable, which is going to be your grade in the advanced functions 12, which is dependent on the number of the hours that you put into that in order to study. It's very easy. You say that if I, for example, study, for example, 25 hours for the whole, I should say, for the whole term, for the final exam, in the function which I decide to predict my score, I may get, for example, 57 out of 100. Then you see what happens if I study 30 hours, 35, 40, 45, until you find the end behavior that it's going to be, for example, 100. And that's the definition of the endpoint behavior. Or you see that the x is going to be large. In terms of, I should say, the math language, you're going to see more of this, I should say, when you go to the next year. You say that if you are going to have your f of x, when you want to see the endpoint behavior, you see that what's going to happen to the function when x is going to be pushed into the infinity. And also, for the sake of completeness, I'm just going to put a sign here, which seems the limit, and that's the mathematical representation of, I should say, asymptotic behavior along the x-axis. Or you see that you're going to see that more in next year, but that's a kind of a brief way to show that what's the function that happens to that when x becomes larger and larger and larger. Look at this one. For example, as an example, it's going to be, let me show a line here, which is going to be this. And I'm going to plot the function like this. It starts from, I should say, for this. And it goes all the way there. It becomes my f of x. It starts from, I should say, it takes a domain from x, all the positive x, and it becomes like this. And imagine the point here, it becomes, for example, any number that it can be. I call that 5. You see that now, visually, we can talk about, to talk about the asymptotic behavior of this function. We say that when the function is going to be, let's say, for example, from x goes to infinity, you see that this model, when you show the function goes like that, it means that the function goes all the way along the x-axis. You can represent this on the x-axis like that. You say that the x of the function is going to infinity, because you see that, for example, you are here and you walk all the way with the functions along there. For example, here, I'm just going to represent, for example, let me plot. For example, look at this. This person here, it's going to be, for example, me. On the x-axis, I'm just running along the x-axis towards this direction. And at any point which I am, I'm looking up to find the value of the function. For example, if I'm standing here and I take a look up there, just right above my head, you see this point? This point, if I read what is going to be the corresponding value of the functions along this, you say that, for example, it can be anything. It can be, if it's going to be, let's say, for example, x naught, the place which I'm standing, this one represents the value of f of x naught. I'm just keep running as fast as I can. For example, I'm just going all the way down there. I'm just going to stand right now here. And still, I just keep going there. I look up there. The value which I read, which is going to be close to the value above my head, which I'm going to read, is going to be so close to the line which is in orange. You see that? Which is the 5. Then this point is getting close to 5. Then the value which I can see, it's going to be the value which is so close to 5, almost to 5. I keep running again. I go all the way down there. Still, I look up. I see again, I'm getting close to 5. You see that, guys? Everyone sees that?
Yes.
That's right. Then we see that the endpoint behavior of the function which I have, f of x, is f of x can be anything. That's this f of x which I'm representing. When x gets larger and larger and larger, and the way we say that x gets larger and larger and larger and larger, it becomes too exhausting. Then I say infinity and cut the thing, and it's infinity, goes to infinity, becomes larger. It becomes what? It becomes almost to plus 5. 5 is what? It's this value which this line intersects the y-axis. You see, and that's essentially, this is called asymptotic behavior. And also, as I said, for the sake of, I should say, completeness of the lectures, not because of, I should say, the things which we need at this stage, I put the limit. Don't bother yourself about the limit. You're going to see that concept next year. But even if we got that, we say that the f of function, if becomes 5, gets close to 5 when x becomes large and large and large and large. That's what we call that asymptotic behavior. Any questions, guys?
No.
No. However, before I just take you to the Desmos to show you some asymptotic behavior, we see, to make some kind of the conclusions, we are going to talk about, I should say, 2 things. For the case of the polynomials that we talked about, I should say, let me change the font. About the polynomials. That we talked. We have 2 types of the polynomials. The first one is going to be even degree polynomials. What is the even degree polynomials? It's going to be very easy. It's going to be this. Look at that. I'm just going to write a polynomial as what we taught before. We said that we say the polynomial is going to be y equals to a x n. I call that subindex n plus a n minus 1 x n minus 1 plus all the way going to a x plus a naught. The thing which you will see there is essentially that's what we talked before. It's going to be the corner, I should say, cornerstone of all polynomials. That we talked about that the coefficient has to be real. And also we talked about the fact that the degree is going to be called this. We said that the n is going to be the highest degree. Then we call that, I should say, the polynomial of degree n, the highest degree, and also we saw that in the lab sessions that we had. But however, we see that also based on the thing that we see that here is that we also have something different here. We see that we have the coefficient of the highest exponents of a variable. This is the thing which we call that, I should say, leading coefficient. The leading coefficient is the coefficients of the highest degree of the polynomials. If n is even number, we call that this is even degree polynomials. However, we can think of, I should say, the odd degrees polynomials, which is going to be our case number 2. When we have, I should say, odd degrees polynomials, it's the case that in our example that we had right now here, we have what? We have, let's say, for example, we say that, for example, if the n is going to be a number, for example, the function like y equals to a3 x to the power 3 plus a2 x to the power 2 plus a1 x to the power 1 plus a naught becomes what? Okay, then it becomes the even power, the even polynomials. Why even? Because you will see that this is 3 is an even number, and a3, which can be any real number, becomes the leading coefficient. Okay, now, in order to talk about the asymptotic behavior of polynomials, it's important to make these distinctions. It is very important to make these distinctions, that our polynomial is either going to be the even degree or the odd degree, and what is going to be, I should say, the leading coefficients. Then remember, this one is very crucial. Okay, we say that in order to talk about this, we just start by, I should say, from the even degree polynomials. With the even degree polynomials, we just want to see what is going to be the asymptotic behavior. Then we say that even degree polynomials with, I should say, with polynomials. Okay, it's going to be fine now. We have two subsets, I should say, of this conclusion. We have the first subset is going to be the case number A. Let's call that case number 1. When a n, I call that the leading coefficient, is going to be a positive number with the even degrees. Then in that case, I'm just going to give an example to you For example, the example is going to be like this, the simplest one which you have seen. We say that, for example, y equals to, for example, I give you an example, 4x squared plus 6x minus 3. For example, it's going to be this very example, the basic example that we have. The polynomials is even degree, and the leading coefficient, what is the leading coefficient? It's going to be 4. It's going to be positive. Let's plot this one, then we talk about the asymptotic behavior when we plot it. This one is an example of all even degrees polynomial when they have, I should say, a leading coefficient which is positive. Let me, I should say, stop the share from here, and I should say share the screen with you on my Google. Look at that. I'm just going to go there to just type Desmos. It gives me to the graphical calculator. And now here, the thing which I want to do, I'm just going to plot that function. What was the function? It was 4x squared plus 6x minus 3. For example, that's going to be our plot. It's a typical example of a polynomial, even degree polynomials with the positive leading coefficients. You see that the function is expanded from, let's say, for example, it's when you just walk along. For example, imagine that's going to be here, for example, Jasper. For example, Jasper is standing here at the -8. He is running so fast towards a positive direction along the x-axis. You will see that when you move towards the x-axis, when x is getting bigger and bigger and bigger, and that's what it means, the asymptotic behavior, you see that the function starts to increase. Sorry, the function gets decreased, then goes to a turning point here, then it goes back again to increase. And you see that the function is expanded from the second, I should say, quadrants. We call this one quadrant 1, quadrant 2, quadrant 3, quadrant 4. You see that 2 points is going to be, both of them is going to be at the quadrant 1 and quadrant 2. Let's plot a different function. Another even polynomials with, let's say, with the positive coefficient. X to the power, let's say, 4 plus 5x to the power 3 plus 7x to the power, let's say, 2 plus x minus 3. Sorry, let's put it to plus 1. Look at this. I'm going to zoom this. To this function. You see that this function also behaves the same thing. Again, it has these expansions from quadrant 2 to goes to the, let's say, quadrant 1. You see that, guys? They have the same characteristics of these functions. Then if you have a polynomials of even polynomials with the positive leading coefficients, as you will see, the function always behaves like that. As a very last example, I say y equals to, for example, x to the power, let's say, 6 minus 2. You see, this function again behaves the same thing. Again, it expands from the first quadrant, goes to the second quadrant. Sorry, the second quadrant goes to the first quadrant. These are the quadrants which they occupy. However, I'm going to contrast it with, I should say, with the polynomials, still even polynomials, but with a negative leading coefficients. For example, imagine this one, y equals to the basic one, 2 times x, sorry, it's negative leading coefficients, minus 2x to the power, let's say 2. Look at these functions. Let me erase the other functions which we have. Again, you will see that the functions which we have, it's even polynomials, because the highest exponents of the x is even number, 2, 4, 6, 8 goes on. But the leading coefficients, which is a coefficient of, I should say the leading coefficient, which is a coefficient of, the highest exponents is negative. You will see that the function, the endpoint behavior or the asymptotic behavior which it represents is going to be something like that. It starts, I should say, from minus infinity, goes to the plus infinity. You see that the function increases all the way going to a turning point. Then as you move along the x-axis, the function decreases. You get minus 4, minus 6, minus 8, and it goes on. Let's have another one. For example, y equals to, for example, minus 3 times x to the power 4 plus 2x to the power 3 minus x to the power 2 plus 3. Okay, let's just focus on these plots only. Guys, look at this. The polynomials which I have is even polynomial. It has to, because its highest exponents for the x is even number, but its leading coefficient is a negative real number. You see that again, it occupies the third and the fourth quadrants, and it has this shape. It has one turning point with this configuration. You can compare this with something which has, I should say, with the even leading coefficient, with the positive leading coefficients, you see the difference, correct? Then you see that these functions have the same characteristics. These functions have the same characteristics. The polynomials, the even polynomials, they have the same characteristics if they have positive or negative leading coefficients and their influence of the endpoint behavior of the function. Everything is fine so far?
Yes.
Nice. Now, so far, I'm gonna stop the share and go back to, I should say, our whiteboard. However, okay, we talked about this one. We talked about the second case. That the second case, we had, I should say, the leading coefficients, in, is gonna be negative. We saw that the function, it always looks something like this. But for this one, with the positive coefficients, we saw that the function always looks something like that. Huh? Now, I'm gonna go, we have only 5 minutes to finish to wrap up the class. Now, we just go to the case that now we talked about the even degree polynomials. We now are gonna talk about the odd degree polynomials. Okay. With the odd degree polynomials, what do we mean? We mean that, for example, we have a function. For case number 1, is going to be this. For example, we say that the leading coefficient is going to be what? Is going to be positive. Let's go to, and also let me show this one also, the second case for all of them. Now the leading coefficient is going to be negative. Okay. Now, Let's, as long as we know that what is our classification, I should say, characteristics. Now, let's go back to, I should say, to the Desmos and see what do we have when we just want to plot them. Okay, now, we know that the polynomials, which I'm just going to plot, is going to be an odd degree polynomials. It means that the highest degree of the polynomial, the highest exponents is going to be an odd number, like y equals to x. It's odd degree polynomials because the highest exponents and the powers of the x is odd number, which is 1. You see that the functions occupies opposite quadrants. We have quadrant number 1 and we have quadrant number 2, which is occupied by the function. Let's go to another function. For example, the basic one, a positive with the positive leading coefficients. The positive is going to be what? 1, x3. You see that this polynomial has, again, the same characteristics. Again, it occupies quadrant number 1 and quadrant number 2. Let's go to another odd polynomials with positive leading coefficients. For example, again, positive 1, x to the power 5. Let's get another one. Let's 4, for example. You see? Another one, y equals to, let's say, for example, 0.5 times x to the power what? Let's say 7. You see that? All share the same characteristics. You see that, guys? All of them share the same characteristics, and all of them, they occupy the third and the first quadrant. Now, you can ask yourself, what about the second, I should say, the second defining criteria that the functions that we have is going to have, let's say, for example, a negative leading coefficients. Like what? Let me erase these ones. At the end, I'm just going to, we want to just compare that. Let's imagine the functions which we have. It's going to be, for example, an odd polynomials with the negative leading coefficients. For example, like -1. -1 is a negative leading coefficient of a polynomial, which is going to be the x. This one, again, is an odd polynomials with minus a negative leading coefficients. You see that the function occupies the second and the fourth quadrants. Let me go back to plot another function. I call that minus x to the power 3. It's like the x to the power 3. Over there, it was an odd polynomials with the positive leading coefficients. It is not with the negative leading coefficients. You see that again, the function which I have, it is essentially occupying again the second quadrant of the Cartesian plane and the fourth quadrant. Let's go to the next one. Let's go to the minus, let's say, for example, 4x to the power what? To the power 5. The blue one. The blue plot, you see again, it has the same characteristics. It occupies the second and the fourth quadrant. And now, as a very last example, the function is going to be like 0.5 x to the power what? An odd number, x7. You see that? You see that green? Then you see that, guys, again, sorry, it's positive, it has to be minus because we are working with the minus leading coefficients. You see that all of them, if I want to zoom out, you see all of these plots, they are essentially occupying the second and the fourth quadrant. Compared to the positive ones, which I'm just going to plot everything right now, you see the positive leading coefficients, all of them, they occupy the first and the second and the third quadrants, but the positive leading coefficients, they occupy the second and the fourth quadrants of the Cartesian the plane there. Everyone sees that? Does it make sense?
Yes.
Awesome. Now I just go back to, before we finish, I go back to my, I should say this one, and I say that, okay, if that's going to be the leading coefficient with the positive leading coefficients, I make it the plot like this. The first and the third quadrant of the Cartesian is occupied. However, if the leading coefficient is negative, my plot may take something like this. It occupies which quadrants? It occupies the second quadrant and the fourth quadrants of my Cartesian plane. Does it make sense to everyone?
Yes.
Fantastic. Fantastic and impressive. Okay. Now, guys, if you have no questions, that's going to be essentially all the things that we had for today. And there is no homework for today, except that we finished the lessons for tomorrow. Then I should say that's pretty much everything. As I have said before, all these lectures are being recorded, either the lab or these ones. You can go back to check that again. And the slides, I'm just going to post it on the course website. Okay.
Okay.
Any questions, guys?
Yeah.
Anki, Laura, Jasper?
Yeah.
Oh, okay. Guys,
No.
then if you have no questions, thank you for today. Then I see you all tomorrow. No homework for today. We start homework tomorrow. Okay.
Okay.
Have a nice day, everyone.
Okay.
Bye-bye.
Take care. Bye.
Bye. Take care, everyone. Bye, Laura. Bye, Jasper.
Bye.